Okay, so we want to solve this problem of me throwing a rock off a cliff with an initial speed of 20 meters per second. So let's see, here I'm on a cliff and it's 100 meters high. So we've got 100 meters. And I shoot it off a cliff, or I throw it off a cliff at an angle of 30 degrees with respect to the horizontal at some initial speed v0 equals 20 meters per second. Okay, so as soon as I see this, I can't help myself. I have to do this. I just have to do this. I have to say, oh, at 20 meters per second, at an angle of 30 degrees with respect to the horizontal, what I know is I have some v horizontal is equal to v0 times cosine of 30, right? And cosine of 30 I know is about 0.87. And so that's about, what, 17 meters per second? I have 17.4. And it has some vertical velocity. Then vertical equals v0 times sine theta. Sine of 30 degrees is 1/2, so this is 10 meters per second. Right? So what we understand is that this rock is going to continue. There's no acceleration in the horizontal direction. This rock will continue on with a constant speed of 17.4 meters per second in the horizontal direction. The vertical direction, it starts out at 10 meters per second, and it's going to slow down because of gravity. It's going to stop at some point. We can recognize it's going to take 1 second to stop because it's moving upwards at 10 meters per second, and the acceleration of gravity is negative 10 meters per second squared. And then it will continue on down and hit somewhere, bam, right here. Okay, so I also know that by symmetry, as it goes up, when it gets back down to this level, it will also be 30 degrees. And when it hits, it's a good bet that this angle, well, it's not a good bet, it's for sure, that this angle will be greater than 30 degrees here. And we have parabolic trajectory. Use conservation of energy to find the speed when the rock hits the ground. Okay, so what does that mean? Well, what I know is that E0 must equal E final. Right, and so the energy I start with is potential energy from gravity, must wind up being that final kinetic energy. And if you did this, you would get the wrong answer, because we need to recognize there is some kinetic energy that we start with, because it's moving already at 20 meters per second. And so now we can put this in and find out, okay, this is mgh plus 1/2 mv0 squared is equal to 1/2 mv final squared. And oh, isn't that nice? Mass cancels. And I can solve for my v final is equal to square root of 2gh plus v0 squared. This is 2,000, and the units are meters per second squared times meters squared per second squared, plus v0 squared, that's 20 meters per second. That will give you 400 meters squared per second squared. Okay? So, and this is to the 1/2 power, is v final is equal to the square root of 2,400 meters squared per second squared. We like the units because the square root of meters squared per second squared is meters per second. But how about this number? Well, I wish it was 2,500 meters squared per second squared, because then it would simply be 50 meters per second. 50 squared is equal to 2,500. and we know it must be slightly less. So let's try 49 squared. What's 49 squared equal to? And this is how I'm going to write it. 50 minus 1 times 50 minus 1. What do you get? You get 50 times 50 is 2,500, right? And then you have plus 1, you put over here, who cares about that? It's very small. But now you have a minus 50 and a minus 50, so it's minus 100. We see that this is 2,400 plus 1. Right? Almost exactly what we want. So we can see that the final speed, I can write it here, is 49 meters per second. Now that we know the absolute value of the speed and the horizontal component, find the angle it makes and express the velocity in terms of speed and angle. Okay, so let's see. What we know is that the horizontal velocity is 17.4 meters per second. That's cosine of theta must be adjacent over hypotenuse is 17.4 divided by 49. Okay, so 17 times 3 would be 51. So that's a little bit high. Yeah, so about 0.3 is about right. And so cosine of theta equals 0.3. So we need the angle, the cosine of which is 0.3. Now there's a number of ways we could do this. One is to remember what cosine looks like. Right, cosine looks like this. Okay, this is 90 degrees. We know that 30 degrees, let's see, we have, this would be 30 and 60. 60 degrees is 1/2. 30 degrees is 0.78. And we're not at 1/2, we're at 1/3. We're down here. And so if this were a straight line, that would be 10 degrees. And this would be 70 degrees here. So it's about 70 degrees. If you use your calculator after you do to check this, I think it's 72.5 degrees. Okay, another way to do this, if we drew 17.4 and we drew 49 at about 3 times that length, 1, 2, 3, about like this, right? We could estimate this angle and we would see that 60 degrees is just a little bit too small for that angle. And we probably wouldn't say it's 80 degrees. That'd be too much. 80 degrees is more. And so 70 degrees is by and large a good estimate. Using Pythagorean's theorem, a squared plus b squared equals c squared. All right, so this is the one we're looking for. Let's call this b. And the hypotenuse is 49 meters per second. So we have 49 meters per second squared is equal to 17.4 meters per second squared plus b squared. Okay, let's drop the units. I'm tired of units. 49 squared, we remember already, is 2,401. And 17.4 meters per second squared. Let's round it down to 17. Make my life a little bit easier. So let's 17 squared then is 289. Okay, so we have 289 plus b squared. Okay, and that's about 300. We subtract that off, then b squared is about 2,100. Okay, great. So we could estimate this again. What squared gives you 21? Well, I could recognize that that's 400 less. That's 400 less than 2,500. And so what if we did 50 minus 4 or 46? 50 minus 4, what would we wind up with? That'd be 2,500 and that's minus 200, that minus 400, plus 16. That'd be 2116, which is reasonably close. So 50 minus 4 is 46, and therefore, yeah, we could say that the vertical component is about 46. The next question says, okay, now how long is it the rock in the air, and find the distance from the base of the cliff that the rock has landed. A quick review of what's going on is that we recognize that velocity horizontal is always the same, is about 17.4 meters per second, right? But velocity, the vertical velocity, is affected by gravity. You know, acceleration is equal to negative g. So we start with 10 meters per second, right? The vertical component of the initial velocity. If we just ask ourselves what happens, after 1 second, gravitational acceleration has brought it to rest, although it's moving horizontally still. The vertical component is 0. After 2 seconds, it's going downward at negative 10 meters per second. After 3 seconds, negative 20 meters per second. After 4 seconds, negative 30 meters per second. After 5 seconds, negative 40 meters per second. And after 5.6 seconds, the vertical component of velocity is negative 46 meters per second. So people who love math will say, I need to see the math. Acceleration is change in velocity over change in time, right? And so the time during this acceleration is equal to the change in velocity over the acceleration, right? And this is just going to be your 46 meters per second minus the 10 meters per second that you started with, divided by gravity, which is 10 meters per second squared. Now let's be careful, because we recognize that it's going downwards at 46 meters per second, and it started upwards at 10 meters per second, and acceleration is negative. So if we do this correctly, we'll get the same answer of the change in velocity is negative 56 meters per second, and so we need 5.6 seconds. Then you ask yourselves, in 5.6 seconds, how far does it travel horizontally? Oh, no problem, because it's moving at a constant speed, so we know that the horizontal distance is equal to, well, your initial horizontal displacement plus v naught t plus 1/2 at squared, right? That's my displacement formula. But horizontally speaking, the acceleration is 0, and we let the initial horizontal displacement be 0. And so this is very easy at 17.4 meters per second times 5.6 seconds. These cancel. We love it because the answer comes out in meters. And now we just have to multiply 5.6 seconds times 17.4 meters per second. Right? We could estimate it with, how about we round one up and one down, 17 times 6 is reasonably close, and we get about 100 meters. So that's about the distance that the rock moves forward on the ground. It's the distance, so that's about the distance from the base of the cliff that the rock lands.